Okay, this video is to show how to compute the vector projection using the dot product. So we're going to draw a vector on here. This will be our origin. We'll make it 2, 1. I'm using these thicker lines as integer coordinates. And we're going to dot it with a vector. We'll call that vector A. So that's A. And we'll put another vector on here. 0.5, 1, somewhere like that. And that's 0.5, 1. Alright, so I want to refresh your memory on how to compute the dot product. So the definition of a dot product of how to calculate it is the like components multiplied together, so ax, bx, and then added together, ay times by. So in this case it's actually 2 times 0.5 plus 1 times 1. That ends up being 1 plus 1 equals 2. So that's not terribly meaningful. We don't know what the 2 means. But we have another definition of the dot product, which is not how we calculate it, but it is equivalent quantity, is the magnitude of A, or the length of A, times the magnitude of B, times the cosine of the angle between them. So here's the angle between them. And we don't know what that is, but we can calculate it using the dot product and dividing by the magnitude of the vectors. But we just want a length along A. What we're interested in is this length perpendicular to A. We're going to draw a line 90 degrees from A. That's going to be this length along A, but only as far as B is pointing along it. If you take a flashlight, some kind of light source, light beams directing at B, but perpendicular to the direction of A, then you see that it casts a shadow, kind of, in this right here. B only extends that far along A. So this length here is actually B, magnitude of B, times the cosine of theta. How do I know that? Let's redraw that triangle here. We'll say this is vector B, this is theta, here's a right triangle. We know that the cosine of theta is equal to the adjacent side, which we're going to call x, the unknown here, over the hypotenuse. And how do I know that? We'll call this length of B here. That comes from SOHCAHTOA, the mnemonic for remembering your triangle relationships. So cosine is adjacent over hypotenuse. Okay, so we solve for x here, multiply both sides by magnitude of B. I'm going to reverse the sides of the equation here. So the unknown value x is actually magnitude of B cosine of theta. Well, we kind of have that in here somewhere, but we've also got it multiplied by the magnitude of A. So in order to get the length that B points in the direction of A, we take, let's write this down, the projection of B on A, this is how we write it, equals A dot B over the magnitude of A, because that's the same thing as magnitude of A, magnitude of B, cosine theta over magnitude of A, and those cancel. That equals magnitude of B cos theta. So that's the side of this triangle here that is the component or the piece of that vector that points in the direction of A. Okay. If we want the vector projection, this only gives us a value, a single value. It can be positive or negative or 0. If you have a vector that points perpendicular to A and you do a dot product, you're going to get 0. And the shining the light test shows that it's not going to cast any shadow on A. Alright, so the vector projection of B on A is very similar to this. This is the value, the length of the vector. If we want the vector projection, we're going to do A dot B over magnitude of A. That gives us the length. Now we need a vector that points in that direction that's unit length. Well, we have A that points in that direction, but it's not unit length. So we can get a unit length vector by normalizing A. So let's multiply it by A divided by magnitude of A. That always gives us a unit vector in the direction of A. Now we can see we can combine these terms. We have an magnitude of A squared on the bottom, so vector projection is going to be A dot B over magnitude of A squared times the vector A. That can also be written as A dot B over A dot A times A. That gives us a vector pointing in the direction of A, which is the length of B cos theta. And that is pointing as far as B is pointing in the direction of A. Now if we did a projection of A on B, we'd have to extend B out, find a perpendicular line to that. That would be A cos theta, be this length here. That's shining the light in this direction. So we'll, have some light beams coming from over here. A cos theta is A dot B over length of B instead. So to project along a certain vector, you divide by the length of that vector after the dot product. To get the vector projection of it, you do the dot product divided by the length of that vector times a normalized vector of that. And you can see once you normalize and you're dividing by the magnitude, that length gets squared on the bottom, so you don't have to take the square root in order to get the length of the vector. You can normalize the vector and you can find the length and divide it out, but if you forget that there's a computation going on in there, you're wasting a little bit of time that could be, that you don't need to do. You don't need to do the square root.